when Albert Einstein first encountered quantum mechanics. He called it spooky. And honestly, that's the word that has stuck. Most of the time when you hear about quantum physics, it's framed as this bizarre, unknowable, mystifying part of science. But does it really have to be that way? Well, it's true that quantum mechanics describes the entire world from you and me to the farthest stars. Its weirdness really only becomes obvious when we zoom in to the microscopic level. One of my goals is to show you that quantum mechanics does undeserve this spooky reputation. At least, not in the sense of being some mystery beyond human understanding. Yes, it's profound, it's mind-stretching, and it's a totally different way of looking at reality. But that's what science does sometimes. When a puzzle seems difficult, the response should be to solve it, not to just give up and call it mysterious. A lot of explanations of quantum mechanics follow a script. They show you something counterintuitive, express complete bafflement, and then maybe, if you're lucky, they try to explain it. I want to flip that around. We're going to prioritize clarity over mystery right from the start. It will still seem strange that, just its nature, but hopefully it won't seem inexplicable. We'll start with the basic experiments that force this new physics upon us, then sketch out a way to make sense of it all, to really get it. Let's first appreciate what came before. For centuries, physics was about understanding what stuff is and how it behaves. The ancient Greeks, like Aristotle, talked about inner natures and purposes. They believed things needed a constant push to keep moving. Then a genius named Isaac Newton came along and changed everything. In 1687, he published his Principia Mathematica, laying the foundation for what we now call classical mechanics. He gave us a crisp, mathematical way to describe the world. Think about a simple rock in classical mechanics. All you need to know is its position and its velocity at any given moment. Newton's laws then tell you its entire future path, as long as you know the forces acting on it, like gravity or the push from your hand. This is incredibly powerful. It's how we can catch baseballs and Land Rovers on Mars. The position and velocity of an object make up its state. If you knew the state of every single particle in the universe, you could, in principle, predict the entire future. This is the idea of a deterministic clockwork universe. It's a beautiful and compelling picture of reality. For a long time, it seemed like we had the basic rules figured out. Then along came quantum mechanics, and everything changed. This was the second great revolution in physics. It didn't just propose a new model within the old rules. It threw the entire framework away. At the heart of this new theory is something called the measurement problem. It boils down to this. What does it mean to measure something in the quantum world? What happens when we do it? And what does it tell us about what's really going on? Believe it or not, there is absolutely no consensus among physicists on how to answer these questions. This has led to a field often called interpretations of quantum mechanics. But that's not quite right. These aren't just different ways of looking at the same thing, like analyzing a poem. They are truly distinct scientific theories about how the world works. In classical mechanics, there's no measurement problem. The theory describes positions and velocities, and you just go and measure them. What you see is what you get. But quantum mechanics isn't like that. The central enigma is simple. What we see when we look at the world seems to be fundamentally different from what is actually there. Let's take an electron. You've probably seen cartoon drawings of atoms with electrons orbiting the nucleus like tiny planets. It's a nice, simple picture. The electron has a definite location and it's zipping around a path, but quantum mechanics tells us something completely different. We can measure the electron's position and we'll get an answer. But we can't predict asterisks. What asterisk that answer will be with certainty. The classical idea of a state, a definite position, and velocity is replaced by something alien to our experience. A cloud of probability. This cloud is often called a wave function. Where the cloud is dense, there's a high probability of finding the electron. Where it's thin, the probability is tiny. So the electron isn't a tiny ball at one specific point before we look. It exists as this spread out potential, this wave function, this cloud of probability. When we measure it, We foresee it to choose a location, but before that, it was a haze of possibilities. This is the jump from the clockwork universe of Newton to the probabilistic world of quantum mechanics. It's a huge leap, but by understanding this wave function, we can begin to strip away the spookiness and see the again, though strange, reality hidden underneath. Thanks for watching, and be sure to subscribe for more.